Okay, let's get started. So today we are going to start trajectory optimization. And so optimization is needed if you have more than one solution. You want to find the best way of doing something. So for example, if you want to move from point A to point B, there are clearly infinitely many paths to go from A to B, but maybe there is an obstacle somewhere here. And then you see that maybe this is the shortest path. And maybe there's an optimal path, which really depends on the dynamics and the geometry. So how do you choose the best path that can be done using trajectory optimization? This obstacle is just one example. You could have a problem where there are no obstacles, but you want to achieve some objectives. So for example, how can you go from, let's say, Chicago to Boston, right? That's a problem involving optimization. There are many paths, not infinitely many, but then there's one path which is probably shortest distance, there's one path which is most energy efficient, and so on. Before we get into a trajectory optimization, let me introduce optimization. So we'll be using some tools in Python to optimize, and we'll introduce that first before we get to trajectory optimization. So the simple problem, so I'm going to illustrate this using examples instead of giving you theory. So let's say you want to minimize a function f of x, x2 minus x1 square plus 1 minus x1 square. Okay, so the optimization variables are x1 and x2, and the cost, or the thing you need to minimize, is f of x. Now, there are multiple ways of doing this. One is you could graph f of x as a function of x1, x2. Okay, and that will be, it'll actually be a surface. And some point that surface will have a minimum value, and that is your optimal value. Another way of doing the same problem is to just simply guess. Okay, in this case, it's easy to guess because you can see that f of x is a sum of squares, two square quantities. If that function reaches a minimum, it will be 0. And if it is 0, then both those things under the square should be 0. So f of x can equal to 0 is what you guessed. This is my best guess. And based on that, I can see that 1 minus x1 should be 0. And similarly, x2 minus x1 square should also be 0. So from that, you can see that x1 equals x2 equals, so x1 is 1 clearly from the left identity. And then x2 should also be equal to 1. Right? And that turns out to be the global minimum. Okay, that is across all x1s and x2s. That will be the minimum. Now, the problem with graphing is it just works for 1-2 dimensions. It becomes harder and harder to graph something beyond 2 dimensions. The problem with guesswork is that for this particular case, is a special problem involving sum of squares. What if it is not sum of squares? We don't know what the minimum is going to be. And so the third method, which is probably the one which we'll use, is numerically solving for the minimum. So third one, numerically solving for the, okay, and that's because I said graphing works in 1, 2, 3D, and guesswork guessing works for special cases. And then we'll see that numerical methods always when I say always work, it comes with a caveat that is you may get a solution, but there's no guarantee it's going to be the minimum solution because the terrain which you see is not like a hill or not like a trough. So it may have multiple hills, and then it's sort of hard to find it. But it will probably give you a solution and give you a better solution than the other two methods. Okay, so what we'll do is we will use, we'll see that there are two types of optimization problems we'll talk about. One is the unconstrained optimization, where you're only minimizing a function and there is no constraints in terms of bounds or limits on the variables. And the other one is constrained optimization. So we'll do A for one unconstrained optimization. And the second one is constrained optimization. Okay, so all these in Python can be done using scipy.optimize.minimize. So we've seen use of scipy before. Inside there is a module called optimize. Within that, there's something called minimize. And there are like lots of solvers which will do constraint and unconstrained optimization. And it's a matter of picking the right one for your particular problem. Okay, so here is the first example. Okay, so that's the solution. X1, X2 is almost 1, as we saw earlier. The way this works is we just have to call, well, first of all, I need to import the scipy.optimize package as module as OPT, and then I do opt.minimize the function. That is that function I need to minimize. I need to give initial guess. I give 1, 2, and then I need to give a method. We'll see what BFGS is in a bit, but then the function has two inputs, x1, x2, they're passed there, and this basically returns the value of f of x, right? You can try something else. Let's try -1, n. And then a good solver will give you the same solution. Now, what is BFGS? BFGS is a method within scipy. So scipy, or just say Python optimize. That's the first one. And it is an example. Okay, so let me search for minimize. That's what I was looking for. Okay, so this is giving the syntax. Scipy.optimize minimize. You need to pass the function. X0 is initial guess. If you have some parameters which that function depends on, that will come next. Then the method. Then Jack, that's a Jacobian. I'll come to that in a bit. The Hessian, the Hesp, bounds, constraints, so on. So you see that you can also have constrained optimization, which I've not talked about, but I'll talk in a bit. Now, what we saw was the method. There are these methods available in scipy. Okay, so we were looking at BFGS. It does minimization of a scalar function of one or more variables using BFGS algorithm. So what is BFGS? I believe if you scroll all the way down, it should, it's not here. I think if you scroll down the previous page, it should have something about BFGS. There it is, method BFGS uses Quasi-Newton, Bryden, Fletcher, Goldfarb. These are people who developed it. It uses first derivatives only and so on. So if you want to really get information about this, what I would suggest is going to saying BFGS, Wikipedia, and there are other resources too. So what we're trying to look for here is what exactly is going on. This is basically the way it is computing the optimum solution. So what you need in order to compute the optimum, you are given an initial guess, and you need to figure out which direction in this case the trough is, right? So what you do is you need to have some sense of the gradient, right? The first derivative. First derivative for one variable is easy to understand, but if you want multiple variables like this one is, it will be called a Jacobian, and we've seen Jacobian in the past. So that delta F gives you the way in which you need to slide down. BK is the Hessian. Okay, what's the Hessian? It's the second derivative of the function or the first derivative of the Jacobian. So if J is df dx, then BK, you usually use H to denote that. It's d square f dx square, if you need to take the derivative of that. And this PK is the step size, so how much you need to go forward. So this is basically what is inside that optimization. It basically tells you which direction to go, and the direction is the one which the gradient decreases the most. And so that's all there, but you don't really need to know too much about that. You just have to know that this is, a person who uses these tools or then develops his own tools, you need to remember that it sort of relies on the first derivative, then second derivative, but this is probably in conflict with what it said here. It uses the first derivative only, right? Why is the second derivative showing up? Well, it turns out that I think it doesn't really use the second derivative, but uses approximation. So it's an approximation of the second derivative. And the reason why it uses an approximation is it's computationally simpler to find the first derivative, because remember we did a finite difference. We had two function evaluations or four function evaluations to find, using one function evaluation, two function evaluations for the forward difference, and I think two evaluations for the central, using the central difference. So using that, you got the first derivative, but the second derivative requires four of those computations, and 4 computations will take more time. So if you're running this optimization, it's probably doing this calculation several hundreds, even thousands of times. So each time you want the Hessian, it means your calculations are going to be scaled by a factor of 4. And that's why you don't want to use a Hessian, and so they use an approximation. So don't worry too much about the terminology. But then it's sort of important to have a sense of what exactly is going on. And I've never programmed any of these algorithms myself, but if I know what is going on, then when there's a problem with these optimizations, I can say, okay, it's because of this, and then I can find another way to do it. Okay, so you can explore other ones. So for example, the easiest way to do it is just take one of this, like CG, and then just put it over here, and then see if it gives you, it gave you to much faster, right? So you can try different methods and see what you get. And I think for a simple problem, it shouldn't be a problem, but when you make it a little harder for it, multiple variables, I think some of them will give you faster or slower solutions, better or worse solutions, and there's something you can explore. Okay, our goal is to minimize the vector x, variable x, but the cost is f of x equals x1 square plus x2 square plus x3 square plus x4 square plus x5 square. Now, if it was a unconstrained optimization, clearly you can guess maybe that solution is all zeros, right? But there are constraints. So subject to constraints, x1 plus x2 plus x3 equals 5. So we guess 0, 0, 0, right? For the unconstrained case, if you put 0, 0, 0, then you'll see that 0 equals 5 is not true. And so it's not a solution. So that constraint adds more complexity to the problem. Okay, then the second is x3 square plus x4 equals 5. Then we want to ensure that x1 is greater than 0.3, x3 is lesser than 5, and then x4 square plus x5 square less than equal to 5. Okay, so here's some terminology. This is the cost. This is basically x1, x2, x3, x4, x5. These are the optimization variables. Okay. This is a linear equality constraint. Okay. This is a non-linear equality constraint. Non-linear equality. Okay, so what's the difference? Well, if you see the first one, it only has, this is no squares. It only involves x1 raised to 1, x2 raised to 1. So that's basically linear. And then the second one is non-linear because even though x4 is linear, x3 is not linear. So anything which doesn't have something which is x raised to 1 or x raised to 0 is called non-linear. So if you have sines and cosines and exponential or whatever, those will be non-linear. Non-linear equality or inequality depending on the sign, the identity, right? And then this is non-linear inequality constraint. Okay, so we still have two more things here. This one is saying that x1 is greater than or equal to 0.3. What it means is that x1 is going to be between 0.3 and infinity. Now you're given the lower bound on it. You're not given the upper bound, so we'll assume it to be infinity. So this is a bound. Similarly, x3 is less than 5. And since there's no bound specified on the lower end, it's minus infinity. So those are bounds. So an optimization problem will have a cost and optimization variables, which are common to constrained, unconstrained. But the constrained optimization will have bounds. It will have linear and non-linear inequality constraints. The good thing about the linear equality constraints, why do we really separate them out, is because the Jacobian of that first equation is very easy, right? You have x1 plus x2 plus x3. So taking the derivative of that expression with respect to x1, we know it's 1. x2 will have 1 and so on. So the Jacobian can be easily computed for a linear equality constraints. It's a little bit harder to find for nonlinear constraints. So the cost, that finite difference, really doesn't show up for the linear equality constraint because it's very easy to compute. So if you have a linear problem, then it's kind of easy to compute these values. The other thing about linear constraints is that the second derivative is 0. And you take the derivative of any of that first expression with respect to x1 twice, you get 0. So it's really nice to have those kinds of equalities. We wish that problems were only linear, but they're non-linear, and that's why we need more complicated algorithms and Hessian and Jacobian to do the computations. Okay, so now how is this problem solved? For a problem like this, it's just impossible to graph. Sorry, impossible to guess. It's possible to graph though, but because there are 5 variables, it just makes it too hard. If it was 2 variables, maybe you could graph it. In this case, what will happen is if it was 2 variables, you see that all your solutions, for example, lie on that hyperplane, x1 plus x2 plus x3 equals 5. That's a plane. And then all your solutions should lie on that. And so that restricts your search space to that plane. Then x3 squared plus x4 equals 5 gives another curve. It's actually a surface. And so we need to find the intersection of of both those and so on. So you can graph it and use that kind of intuition, but I still think it's very hard to do this by graphing. So if something like a numerical technique will always work. So I'm going to show you two methods to do this. There are two algorithms there. We use the same function, minimize, but we use it in using two different methods. So here is one of them, and I've written another one. Okay, I've written two because, as you'll see, the syntax is slightly different. So I'm going to run this first. So it did some computations. It gives you some information about the optimization, but this is the solution as per the. Let me just save this. As per the method I used. Okay. And then I'm going to run this using another method, and I'll show you what this method is. And this is the result. So let's just copy that. I'm just trying to see if I get the same answer using both methods. Okay, so do you think they're the same? Look pretty close. The last one is 1e negative 8. That's almost close to 0. Second one, that's also close to 0. So it looks like they're giving you almost similar answers. So both those methods give you the same answer. Now, it's a different issue if that's the local or the global optimum. Local optimum means that optimum is in the vicinity of the guess, and global optimum means no matter where you search, that's going to be the minimum. And that happens only because if the function has a lot of bumps, then sometimes the optimizer doesn't give you the global optimum. Okay, so how are these different? Well, let's look at the minimize function. In one case, I'm using a method called slsqp. In another case, I'm using a method called trust, constrained. I think that's what it means. Let's go to the documentation and try to locate it. Okay, so here are the methods. I used trust constrained, and then I used slsqp. Okay, so why did I use these two given the list of all the other options? It turns out that the scipy.optimize only has three methods to do constraint optimization. And so those should be here. So you can see unconstrained minimization. It tells you that these are the methods available for unconstrained minimization. You can use any of these. However, when you go to bound constraint is when you have, I believe, when you have limits on x1, x2, so on, then you can use bound constraint minimization. But if you want to do true constraint minimization, like you have these five subject to conditions, then you can use COBYLA, SLSQP, and trust constraint. Now, I couldn't use this one because I think it requires based on linear approximation of this. So it doesn't use the Hessian. That's my understanding. I think it will not give you good solutions, or maybe I'm wrong. Maybe I should try this. I really didn't explore this one. SLSQ is based on sequential least squares programming. It's also called sequential quadratic programming. And this one is trust region algorithm. And then there is some information about it. If you want to search for it, you just go and type sequential or SQSLP. I don't know if that will lead into where it is. I would just search based on its name. It's called sequential quadratic programming. And then it gives you information about what exactly it does. Minimize f of x given constraints, like so. It basically constructs this L. You've heard of Lagrangian before, right? There's a Lagrangian which we saw for dynamics. There's also Lagrangian for optimization. It basically has the cost Remember that was our T minus V. And then the lambda and sigma are here Lagrange multipliers. Same thing we saw with constraint forces. B of x, C of x are our constraints. So this is how it is cast. This is actually exactly how the equations of motion are derived from. When we're trying to solve for the equations, we are minimizing the Lagrangian subject to the condition that those constraints are met. That is, the forces keep those points, whichever the robot makes in contact, stationary. And then it basically computes the, I believe the first derivative, it computes the approximation of f of x. So that approximation here is based on the Jacobian, delta f, and then the Hessian, delta square f, so d square f dx. And then it also approximates the constraints using the Jacobian. And then there is like, this is just the start, and then you figure out how to update D. Every time it's trying to update D. What is D? D is basically the step size you need to update the solution. So if you're at a particular point X and figure out which direction you want to go down, and then you also have to figure out the step size. The trust constraint is another optimization method which is based on minimizing approximations. Again, the same form. It looks different, but G is basically Jacobian, B is the Hessian. I think it's an approximation. And then it just uses a similar method. Just depends on how you update the direction, and step size defines what method you use. So, okay, so that's the theory. Don't worry too much about it. I think it's important to know that what goes inside in case you're not able to get the solution, but I don't think you need to know more than that. So how exactly are they different? Turns out that these have to be written in different ways. So for the SLSQP, I need to supply the constraints as a dictionary. This is how a dictionary is defined: type, inequality, equality, and then the function. One case of the trust constraint, I specify them as objects: Jupyter linear constraint, nonlinear constraint. Another thing to note is that for this method, the constraints are all put together, and we don't really distinguish between linear and nonlinear constraints. I have taken the attempt to distinguish them, but the software doesn't, or the method doesn't really require you to distinguish between linear and nonlinear constraints. However, if you look at this one, you actually have to tell it what the linear constraints are, what the nonlinear constraints are. Now, the good thing about telling it that these are linear constraints, that it can use smarter methods to solve for these problems. So for example, we know if it's linear, then Hessian is 0, so you don't have to even bother with that. It just has to compute the Jacobian. Okay, and then what are the things which go with the limits? They are specified here as an object. And then here they will be specified as a dictionary. No, it's specified as an object, not as a dictionary. The constraints are as a dictionary. And then the same again, cost as a cost is a nonlinear function which goes inside here. And then it just prints. Okay, so you should know how to use it. And then if it doesn't work, then you should be able to use another method. And then you should also understand why you want to use, say, BFGS versus SLSQP. You can use SLSQP for unconstrained optimization, but you cannot use BFGS for constrained optimization.